Hi girls, and welcome to another video looking at redox chemistry. This is going to be the penultimate video in our series on redox chemistry, and today we're going to look at how we can identify what's being oxidized and what's being reduced when we have an electrolytic reaction occurring in an aqueous solution. I alluded to this in class the other day, and I would like to get into a little bit more detail about it. So, when we have an aqueous solution and we're undergoing an electrolysis reaction in that aqueous solution, we need to consider what we've got present. So in an aqueous solution, we have two sets of cations and two sets of anions. We have the anion and cation that come from the electrolyte or ionic substance that we're dealing with, and we also have hydrogen ions and hydroxide ions from water. So when we consider, say, a solution of sodium chloride, our cathode is negative, so our cations, sodium and hydrogen, are going to be attracted to that cathode. The anode is positive, so the negatively charged anions are going to be attracted to that, which means that the chloride ions and the hydroxide ions are going to be attracted to the anode. So both of those things are happening. So when it comes to deciding which one is going to react, we need to consider the standard reduction potentials of the species at each electrode. This process is sometimes known as selective discharge, which means that one species or the other is going to be oxidized or reduced in preference. Okay, so let's look at it in a little bit more detail. Firstly, we have the anode, and at the anode, both hydroxide ions and chloride ions are going to be attracted to the positively charged anode. There are two possible reactions that could be occurring in that case. Obviously, at the anode, oxidation occurs. So we could have our chloride ions being oxidized to form chlorine gas, and we could have our hydroxide ions being oxidized to form oxygen gas. Both of those could be happening. And what I've provided you with is the standard reduction potentials for the reverse reduction reactions. So when you want to figure out what's actually happening in your system, the first thing you want to start with is the observations. Okay, that is more important than anything else, because if you are smelling a pungent gas that smells like the swimming pool, then you know you must have chlorine gas being formed. Similarly, if you have bubbles of gas but no odor, then it is unlikely that chlorine gas is going to be formed. And you could test the gas that's being formed using a glowing splint, because oxygen gas obviously will reignite a glowing splint. So that's the first port of call. And your observations are the most important thing. It doesn't matter what all the calculations in the world might show if that's not what you're actually observing. If you're actually observing chlorine gas being formed, then that's what you need to be talking about in your reaction. The second thing you need to consider is the relative concentrations of both species. For example, if we have an aqueous solution of sodium chloride, particularly if it's a reasonably concentrated solution, then we're going to have a lot more chloride ions than hydroxide ions, around about 100,000 times more chloride ions than hydroxide ions. So when it comes to ions being attracted to that anode, there are going to be a lot more chloride ions there than there are hydroxide ions. However, there's one other thing that we do need to consider, and that final thing is the standard reduction potentials. See, if we have a look at these, then these are oxidation reactions, so we need to look at the strength of these two substances as reductants, okay? Because obviously the reductant is the thing that's oxidized. And hydroxide with a lower E naught value is a stronger reductant than chloride with a higher E naught value. Therefore, we would have to say that hydroxide ions would be more likely to be oxidized than chloride ions, all things being equal. So that's the first thing to consider. So that, in this case, we would expect that hydroxide ions forming oxygen gas would be the reaction that's occurring at the anode. So that's our first half equation to consider. At the cathode, we've got sodium ions and hydrogen ions, and they're both going to be attracted to the negative cathode. And again, we've got two possible reduction reactions occurring. We've got sodium ions being reduced to form sodium metal, and that has a very, very low E0 value. That means it is going to require a lot of energy to make that sodium metal be formed. We also have hydrogen ions, which can be reduced to form hydrogen gas, and that is going to have an E0 value of 0, which means that the hydrogen ions are a much stronger oxidant than sodium ions, so are much more likely to be reduced. Again, though, you should start off with your observations. Are you observing any sodium metal being formed, or are you observing bubbles of gas forming at the electrode? So that's your first starting point. Now, based on those standard reduction potentials, hopefully it's easy to see that the hydrogen ions are much more likely to be reduced than the sodium ions, and therefore that's the reaction you would expect to see happening at the cathode. The other thing to consider at times is if you have polyatomic ions present in your aqueous solution, such as nitrate, sulfate, or carbonate. Those anions would be attracted to the anode. And at the anode, of course, oxidation occurs. However, the nitrogen and nitrate, the sulfur and sulfate, and the carbon and carbonate are already in their highest possible oxidation states. So the nitrogen is +5, the sulfur is +6, and the carbon is +4. So because they're already at their highest possible oxidation state, it is impossible to further oxidize those species. Okay, so when you've got nitrate, sulfate, or carbonate, you cannot further oxidize those things. Similarly, if you've got ammonium present, that would be attracted to the negatively charged cathode, but nitrogen already has an oxidation state of -3, so it's not going to be reduced any further. So if you've got those ions present, you know they're not going to be oxidized or reduced as appropriate. So therefore, whatever's present in the water, the hydrogen and the hydroxide, those are the things that are going to be oxidized or reduced when you've got these ions present. Okay, so we're going to do some more practice on this when we get to class, but I just wanted to go through this in a little bit more detail. This is just about the last thing that we need to cover in this class. So my final video will be just looking at a few bits and pieces for the assessment. I'll see you soon, girls. Thanks, bye.